Welcome to this requested special edition Simultaneous Equations, one linear and one non-linear equation. Fingers crossed, by the end I'll have demystified the general idea about simultaneous equations with having one linear and one non-linear. One of the interesting things about maths is the amount of language they use. And just some of the important language I'll try and talk about now is the idea of intersecting, quadratics, linear and non-linear equations. But maybe the first thing that's important is to look at what actually a nonlinear and linear equation is. Well, we've sort of met these before in some of my other videos, because linear, if you actually look at the word linear, what does it mean? It starts with the word line. So actually, that's pretty much that. Anything that can be drawn with a straight line is called a linear equation. And these generally have the form y equals mx plus c. So y equals 2x plus 6, or y minus 2x equals 6, or any variation of that will give you a straight line. That's the equation of a straight line. Things that are non-linear, I suppose just by the general definition of what a linear line is, means that if it's non-linear, it's not a straight line. One of the types of the non-linear graphs we tend to get quite a lot are quadratics. Now, the general form of a quadratic is a U-shape. And it has the general equation of y equals x squared. But that isn't by any means the be-all and end-all of what a quadratic can look like. And maybe it would be quite useful to do a quick recap of quadratics just so that we can, I don't know, just visualize. Because sometimes the idea of simultaneous equations, if we can see what we're doing, then life becomes easier. This shape here could be a basic quadratic. It could have the general form of the equation y equals x squared. And in fact, the chances are we could say that that actually is. Now, we can actually, by just doing something relatively simple in terms of algebra, get different types of quadratics. So if I was to have the graph of y equals x squared plus 2, and a little bit of this learning is outside of the scope, basically what that actually does is move the whole graph up 2 places. That's right. The whole graph has literally just been translated up 2 places. Exactly the same shape. So it would appear that this value here moves the graph up 2. What would happen if I wanted to have this graph, for example? Well, if we assume that actually that's moved down 3 places but still has the general form of a quadratic, then x squared minus 3 gives me my quadratic. Right? So this number on the end moves the graph up and down. How would I move it left and right? Well, this is an example of moving a graph to the left. If we were to look at the equation of that graph, we'd probably end up with something like y equals x plus 4 squared. This means that our crossing point here would actually be at negative 4. Well, that seems a bit weird because we've got a plus 4 inside our brackets. Well, yep, remember that that's our first graph, that's y plus 4. Look what happens if I have this graph, right? So let's turn off the other 2 and just see what this graph is. So this graph over here actually could have the equation of y equals x minus 3 squared. And generally speaking, the number inside our graph does exactly the opposite of what we're expecting because it's in by the x. What we know is that actually the graph moves in a horizontal sense, but a minus 3 actually moves it that way 3 places, and a plus 4 actually moves it that way 4 places. Well, because maths is this massive fat trick, they actually will try and trick us because we can write quadratic equations in lots of different ways. And the general form of a quadratic equation, hopefully you know this, is that y equals ax squared plus bx plus c, or it has an x squared term, an x term, and a constant. The a, b, and c are just different values. So how could the graph y equals x plus 4 squared look like this? Well, you just multiply it out. You do FOIL or whatever you actually do to get, but you know, again, beyond the scope, I know that that can be written as x squared plus 8x plus 16. And so once again, yeah, that's in the form of ax squared plus bx plus c, where a would be 1, b would be 8, and c would be 16. So if we now look at all of these graphs all on at the same time, then all it is just a graph that's been moved around. How does that help us with this idea of linear and non-linear, and more important, quadratic equations? Well, what is a quadratic equation? Well, hopefully in its basic form, that could have the formula of y equals x squared. What about if I now add another line on? Well, that could, for example, have the equation y equals 3x plus 5. What are simultaneous equations? They're actually nothing more than where two graphs effectively cross. So we can see now that this graph crosses at this point here and this point here. What does that have to do with the price of fish? I can hear you scream, or probably not, because you probably don't know what the price of fish has got anything to do with anyway. But actually, what it tells us is, at these 2 points, something very special happens. We know that the y values are the same, and we know that the x values are the same. And we use that interesting little trick to help us then solve the values, because where the y values are the same, we now know that if these two values here are the same, then we know that this here is also the same. And we can start equating things, and we'll do that a bit later on. But actually, simultaneous equations being that interesting trick may give us a situation where, for example, the line only touches the axis in one place. Well, let's have a look at that. If I now draw that line on, it could, for example, have the equation y equals 5x minus 2. But what we actually notice this time is that it seems to only touch the graph in one place. Doesn't matter, you still use the same ideas, but what you actually probably will find out is that there will only be one value of x and one value of y. And to take this to its logical conclusion, that line there, actually this third line I've now added, has absolutely no intercept, and as such the equations won't be able to be solved. So again, when you are looking at simultaneous equations, what you're actually doing is you're looking at the ideas of where graphs cross. Well, let's now look at an idea where we can actually put this into some sort of algebra. We now know that these equations are looking at where the x values and the y values are the same, right? Keep that in mind. We're looking at the point where the x values and the y values are the same. So if I write them out, just to keep my board clean, we've got y squared equals x squared minus 1 and y equals 5 minus x. Well, remember, we're looking for where x's and y's are the same. Now, we love writing equations like this where we have one letter equals, because what I know is that the y values are the same. And in maths, if these two are the same, it means that these are also the same. And in maths, if they're the same, we put them equal to each other. So I can now say that at the points where they cross, we have x squared minus 1 is equal to 5 minus x. Whoa! We're almost there. We look at this situation here. How many unknowns do I have? I only have one unknown. And when I have an equation, if I've only got one letter I don't know, I can find ways of solving that. Well, firstly, we need to do some rearranging, because this is a quadratic. We know it's a quadratic because it's got an x squared term in it. And to be able to solve quadratics, we generally want to get it in the form of ax squared plus bx plus c equals 0. Which means that plus 5 has got to move over here, and the minus x has also got to move over there as well. Well, what does that give us? Well, the x squared minus 1 were already there, so we'll just move them to the front of the queue. A positive 5 over there becomes a negative 5, and a negative x becomes a positive x, and lo and behold, it becomes equal to 0. A little bit of simplification, we get, I'm going to write my terms in order now, so there's my x squared term used, I've got a plus x term, that's that used, and a minus 1 minus 5 is minus 6, that's equal to 0, and now I have a quadratic. What I'm about to do, there are 3, 4, a billion different ways of finding the answers, but what I do is I do something called the T method. I'm just going to do it, and hopefully you'll follow, but what I suggest is solving quadratics is again outside the scope of this, but what I do is I was taught the T method, and what you do to do the T method is you do the number in front of the x squared term times the number on its own, the constant. So bearing in mind that's a 1, I do 1 times minus 6, and we do minus 6 over here. And what we actually do now is we sort of forget the question, because having got minus 6, I need to try and find the factors of minus 6. So I get 1 and 6 and 2 and 3 and 3 and 2 and 6 and 1. Basically, these numbers by pairs multiply to give 6. So what I'm now going to do is to make them minus 6, I'm just going to turn the minus down into one of these columns. Why on earth have I done this? Well, I've used this term and I've used this term to get to my t method. What is this number in the middle? Well, this number here is a plus 1. And what we're trying to do is we try and find a pair of numbers here that actually add to give plus 1. Well, that's minus 1 and 6. Nope, that's no good. Minus 2 and 3, that's 1. Is there another one? Minus 3 and 2 is minus 1. Minus 6 and 1 is minus 5. So actually, we use this pair of numbers here to help me expand my brackets. If you're already lost, trust me, I'll do another video on this at some other point. But the x squared stays and the minus 6 stays. And what I do is I'm basically doing this to try and split up plus x into two terms. And I know that I can write that as minus 2x, because there's my minus 2, plus 3x, because there's my plus 3. Have I changed the equation? No, I've added an additional term, but if I look at minus 2x plus 3x, it still gives me that. Why do we do this? Well, we now start considering things in terms of pairs. Because I've got an x squared minus 2x, and if I look at factorising that pair, I can see I can take an x out, which gives me x minus 2. And if I look at this here, I've got a plus 3x minus 6. I can take plus 3 out, and what does that leave me? X minus 2 equals 0. It shouldn't really now be a coincidence to notice that actually I've got two brackets with x minus 2 in it. And what does that mean I can do? I can factorise again. Because what I've got is I've got a term here and a term here. So if I take out my x minus 2 out of a set of brackets, then what I get is an x left and a plus 3 equals 0. And using what we call in Australia the null factor law, we can now say that that means that x minus 2 equals 0 or x plus 3 equals 0, which gives a value of x equals 2 or x equals minus 3. Now you might think, well, I've reached the end of the question, I've got no idea what I've done because I seem to have lost the plot with regards to simultaneous. Actually, that's what you've done. You've done a simultaneous equation. You've solved it, but in a slightly different way, simultaneously. And what you've now found is you found the 2 points where they cross. Remember, this top graph here is nothing more than a quadratic that looks like a U shape. This graph here is a graph that goes down like that. So now you have found the two x values where they cross. It crosses where x equals 2 here and x equals minus 3 here. So I have my two x coordinates as x equals 2 and x equals negative 3. How do I find my y values? Well, using this last equation here. Y is equal to 5 minus x, so y is equal to 5 minus 2, gives me 3 for my y value, and y equals 5 minus minus 3 gives me 8 for that value. And so my answer would be written as coordinate number 1 is 2, 3, and the next coordinate is minus 3, 8. There we go, I found my two crossing points. Here we have something that looks a lot more complicated, right? Y equals 2x squared plus 12x minus 4 and y equals 2x minus 1. Well, solve them simultaneously. Well, that's not that difficult either, because once again we've noticed they've made it nice and easy for me. Lovely. Y equals. What do we know about simultaneous equations? We know that where two graphs meet, the x values and the y values are the same. So we know that because the y values are the same, the x values must also be the same. How does that mean I can write it out? Exactly as we did before. So I can now write that 2x squared plus 12x minus 4 is equal to 2x minus 1. We can only solve this when we have it in the form of ax squared plus bx plus c equals 0. So we need to do a bit of shufting around. Plus 1 moves over here and the 2x moves over here as well. So the 2x squared was already there, plus 12x. minus 4, again, was already there, minus 2x plus 1 equals 0. Bit of tidying up, 2x squared, that's that done, I've got no more x squared terms, plus 12x minus 2x is plus 10x, there you can go, and minus 4 plus 1 is minus 3, which equals to 0. So how do we solve this? Well, looking at our t method, let's draw our t, and it's the first number times the last number, which is minus 6, which just happens to be the same as the last time. And so we have 1 and 6 and 2 and 3 and 3 and 2 and 1, 6 and 1. And one of those is a negative, and before I go any further, I probably can see an issue because there is no way that any of these numbers here are going to add to make 10. So unfortunately, in this situation, we can't actually use the t method, which means we have to come up with one of our other ways of solving a quadratic. And I think probably the best we're going to use is the quadratic formula, which is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Now hopefully again that's not new to you, but we use the values of a, b and c from the equations, where a is 2, b is 10 and c is minus 3. So substituting values into the equation, we get minus b, which would be minus 10, plus or minus the square root of b squared, which is 10 squared, minus 4 times 2 times negative 3 all over 2 times a, which is 2. Let's do a bit of tidying up. Minus 10 plus or minus the square root of, well, 10 squared is 100, minus 4 times 2 times minus 3, well, minus 4 times 2 is minus 8, minus 8 times minus 3 is 24, divided by 4, and so that becomes minus 10 plus or minus the square root of 124 divided by 4, which gives an x value or x1 value of 0.284 and an x2 value of minus 5.28. Now again, the fact we've got two values means it crosses in two different places. Does that make sense? Well, I suppose so. Again, we had a quadratic and a straight line intersecting, and so the chances are there will be two. Having got my x1 value, how do I find my y1 value? Well, again, use the formula that if x is 0.284 and y is equal to 2x minus 1, then my trusty calculator tells me that that value works out to minus 0.432. And again, if if x2 even is minus 5.28, then my trusty calculator suggests that my y2 value is minus 11.56. Now that seems horrible, but again it isn't, because when both equations are equal to y, you put these two things equal together, do a bit of shifting around, and then use whatever tools you've been given to solve quadratic equations. One more example. Right? Here, again, maths is just trying to trick you. Now, you don't have anything x equals or y equals. They're just trying to ramp up the level of complexity. So how do we actually solve this? Well, we've got the curve x squared plus 8y equals 8. How many unknowns are there in that equation? There are two unknowns. Now, if we have an equation with two unknowns, I can't really solve it without having two equations, and that's just called simultaneous solutions. How do I actually turn this equation so that I've only got one unknown? Well, it means I've got to get rid of that y. Or, the flip side, I've got to get rid of that x. I've got to choose which one do I get rid of. And that sort of comes with experience. I know that's very easy for me to say, but looking at this at the moment, the only way I can get rid of a letter is to use the other equation. So I've got x plus 2y equals 2. So I can now move the plus 2y over here and get x is equal to 2 minus 2y, So we get an x on its own, that seems quite nice. Or if I want to get the y on its own and have x plus 2y equals 2, get the y on its own means I've got to move the x over here. So we get 2y is equal to 2 minus x, because it's a plus x on this side, becomes a minus x. And then divide everything by 2 gives me 2 minus x all over 2. Now, having got these both here as either an x equals or a y equals, let's see what happens when we substitute either one of those. Now, I'm pretty sure you already can imagine you don't want to substitute for a fraction because that's just going to look horrible. So we have x squared plus 8y equals 8. And let's just do a dividing line down here so I don't get too confused. X squared plus 8y equals 8. Right, well, we know that x can now be replaced with 2 minus 2y. I'm replacing one letter with more than one letter, so we put it in brackets. So we get 2 minus 2y squared plus 8y equals 8. If we now try and do the same thing over here, where we have x squared plus 8y equals 8, but now we're substituting for y, and again we've got more than one thing, that would give us x squared plus 8, and in brackets, 2 minus x all over 2 equals 8. Don't know about you, that doesn't look particularly nice. And perversely, actually, it's sort of easier than it looks. But we'll stick with this idea because I don't have a fraction. I don't have to worry about fractions. I'll stick with the idea that I've got. So we're now going to multiply out this bracket because we can. And what am I going to get? Well, I'm going to get 2 squared, which is 4. 2 times negative 2y is negative 4y, which I double, which is minus 8y. And minus 2y squared would give me plus 4y squared. Plus the 8y equals 8. Can I make anything simpler here? Yep, because the minus 8y and the plus 8y cancel. Now in this case that's a bit of a fluke and we're very lucky that that happens. And what do we get? We get 4y squared plus 4 equals 8. Now you might be tempted to move the 8 over and start going, well, okay, I can make that, but it's a bit of a trick. You don't have to solve this using quadratics. I'll tell you why. Because you only have a y squared term. You don't have another letter, and so once again, it's just a bit of a big fat trick. So I have 4y squared, because I'm going to move this plus 4 over here, is equal to 8 minus 4. So y squared is equal to, well, 8 minus 4 is 4, sorry, 4y squared is equal to 4, and just moving over here and using a bit of this space, what do I get? Well, that gives me that y squared is equal to 4 divided by 4. Y squared is equal to 1, which gives me y is equal to plus or minus 1. Now, I hope you realize that when you square root, you get two values. All right? A lot of people make a mistake here and they just get one value. So having now got two values of y, where I've got y1 is equal to plus 1, and y2 is equal to minus 1, I go back and use my equation here and say, well, let's do some substitution. So if I have x plus 2y is equal to 2, and I know that y is 1, then x plus 2 equals 2 must give you x is equal to 0. And what happens here? Well, again, x plus 2y equals 2, but in this case y is minus 2, gives x minus 2 equals 2, so x in this case must be 4. And there we go. I have two values once again. I know that my crossing points are at 0, 1, because there's my 0 and there's my 1, and I have my other crossing point at 4, minus 1, because there's my 4 and there's my minus 1. Now again, just a word of warning, obviously when you work things out with y equals, a lot of people make mistakes and they try and write the coordinates down as something very silly as 1, 0 and minus 1, 4, because that's the order in which you've worked them out. Don't confuse yourself because obviously the x value always comes first, so this is silly. Well, hopefully that's actually helped. If there's anything else you need, let me know. Hopefully this has demystified simultaneous equations just a little bit for you.